Welcome back to Applied Algebra and Trigonometry. This is part B of the More About Functions lesson. Let's do a quick analysis of these two functions before we move on. So looking at the first one, the domain and the range, we have some different things we need to consider. We have two parts to this, two terms. For the first term, where we have 1 over v, v cannot equal 0. It can be negative, it can be positive, it just cannot equal 0. Can v equal 0 under the radical sign? The square root of 0 is 0. Yes, that works. However, negatives do not work under the radical sign, so v has to be greater than or equal to 0. Since 1 over v and the square root of v are part of the same function, we have to limit the domain to all real numbers v greater than 0. And what would the range be? From our previous analysis of 1 over an independent variable, we know that that can never equal 0. And we've already said that the independent variable itself can't be 0. So even the second part here of the function, the second term, is always going to be a little bit greater than 0. Therefore, the range here is all real numbers s of v greater than 0. Now let's look at the function u of v. Now don't let the negative under the radical throw you, because you're right, that is a negative, but we don't yet know what v is. If v is a positive number, then the negative will make it negative. You'll have a negative under a radical. Can't have that. So v cannot be positive. Could it be 0? Yeah, because the negative 0 doesn't really mean anything. It's still 0. So square root of 0 is 0. That's good. What if it's a negative? Let's put in a negative just to see what happens. Let's put a negative, 4 in there just so we can do the actual square root. Okay, so the square root of the negative of, remember the variable, putting it in parentheses. Here's a night where it's a good idea to put in the parentheses first and then insert the value of the variable. So here we go. The square root of 4 equals 2. So if our independent variable is negative, it works. Or if it's 0, it works. Therefore, the domain for the function u of v is all real numbers v less than or equal to 0, because everything less than 0 is negative. Negative works. Okay, what does that mean for the range? Will we ever get a negative from this expression? No, because remember, if you are given a radical, a square root, as part of your original function, you do not consider the negative square root. It's always the positive square root. So v is always going to be greater than or equal to 0. You're going to ignore the negative. So now let's look at another type of function called a piecewise function. Here is an example of a piecewise function, and it's in pieces. It has the value 0 if the independent variable is less than or equal to 0. It has the value 10.80 for x between, greater than 0 and less than or equal to 10. And it has 1.08 times the independent variable for x greater than or equal to 10. That looks pretty strange. Does that have a real-world application? Actually, yes. Some restaurants have a minimum $10 charge if you use a credit card. So if you buy a $3.95 appetizer, they will charge you $10. And the tax here in New York State will bump that up to $10.80. And then, of course, you keep applying tax as you buy more expensive entrees. Let's talk about the domain and range for this piecewise function. Okay, and this is just one piecewise function. All three of those pieces define one function, f of x. Now, one way to examine a piecewise function, or the graph of a piecewise function, is to take a vertical line and drag it from the negative x values to the positive x values, imagining you're going from negative infinity to positive infinity. And when do you first hit the graph, the x values in this graph? Well, way before the edge of the screen here. The domain here out to negative, it goes out to negative infinity. You're not paying anything until you hit be above 0. At 0, you're still paying nothing. But then as soon as you move just the tiniest fraction above 0, you buy a penny candy, boom, you're going to pay $10.80. It jumps right up there. But 0 does have a value, and just a little bit positive, just to the right of 0, has a value, and all the way out to positive infinity. If you're a billionaire, you can buy a lot of food there. It's all in there. Okay, so the domain is all real numbers. Let's take a look at the range, though. Let's do a similar type of analysis with the range. So we're going to start toward negative infinity. Where do we first hit the graph? At 0. So there's nothing. The range does not extend below 0. The range is going to start at 0. So right now we have all real numbers. We want to make sure we remember we are only dealing with real numbers. So we have all real numbers. F of x is equal to 0. Do we have less than or greater than here? Well, let's take a look. We have equals 0, nothing else. Well, that's all we have in this part, or this piece. But look, if we keep moving our line up, we hit the graph again here. There's just nothing in between. So x either equals 0 or it's in this other part of the graph, and that's exactly what we write. We write or. We write 10.80 is less than or equal to f of x, because in this second part of the piecewise function, it either equals 10.8 or or it keeps going up. But let's do a little bit of evaluation of this piecewise function. Let's look at what happens if you don't spend anything, you don't buy anything. You just walk in, you decide you don't like look at the place, you walk out. How much do you spend? Well, for x less than or equal to 0, we come up here, we check out where our x is. Our x is equal to 0. So what does the function return? 0. Okay, let's say you go for that $3.95 appetizer. I'm leaving out the dollar signs here. Okay, where does that fall in our piecewise function? Well, it's greater than 0 and it's less than 10. So it's right here. The function returns 10.80, $10.80. You're going to pay for that. Okay, what if you spend $15 at this place? Okay, where does $15 fall in your piecewise function? Well, it's greater than 10, so you're going to spend 1.08 times $15, which is equal to $16.20. So at the end, if I were doing an application problem, when I got down to my final answer, I would insert the dollar sign, because you always want to report units on application problems if you are given units. All right, here's another piecewise function, the function p of r, that equals 1 over r for all r is greater than 0, and it equals -2 for r equals 0. So first, before we do domain and range, let's evaluate this for some different values of r. Let's find p of, 10. Okay, so where does 10 fall in this? 10 is greater than 0. So we're going to use this formula for the function. So we will have 1 over whatever r is. In this case, r is 10. So that equals 1/10. Okay, let's look at the function p of 0. Where does that fall in our definition of this function? Well, if r equals 0, p of r equals -2. All right, so let's look at a negative number now. P of -3. Where does that fall? Is that r equals -3, greater than 0? No. Is it equal to 0? No. So it is undefined for this function. This function just does not deal with negatives. Now be careful, because 1 over r in itself, you can stick some negatives in there for r, and you will return a real number. In fact, you just can't do it for 0. For any other real number, you could do it. However, our function is limited to r greater than 0 or r equals 0. So piecewise functions do not just depend upon what the formula is, but here the function actually tells you the domain for which it is defined. In this piecewise function, the domain is all real numbers r greater than or equal to 0. And the range is all real numbers, but what are the constraints on the values of p of r? Let's check the zone f numbers and see if that will give us some clues. For z, we have 0, and the function p of 0 is defined here, where r equals 0, it's equal to -2. Okay, let's do 1. The function of 1. 1 is greater than 0, so we're up here. 1 over 1 is 1. Let's look at -4. Where does it fall in here? Is it equal to 0? No. Is it greater than 0? No. So this is undefined. Can't evaluate that for negatives. Nothing negative will work. E is next, so let's choose an extreme function. I chose 1000. The function p of 1000 is 1,000th. So that's a tiny number. It's getting close to 0, but it has not reached it. Let's do a fraction now. Let's do 1/10. Where does 1/10 fall? Is it 0? No. Is it greater than 0? Yes. So 1/10 will go in here for r. And when we do that, we will get 1 over 1/10. We're dividing by a fraction. That's like multiplying by the reciprocal. So we will get 10. So by looking at these zone F numbers, what do we see? Well, we see that it cannot be negative. R cannot be negative. The function of r, if that happens, it's undefined. Okay, we already limited r to being greater than or equal to 0. So actually, because it is defined this way already in the domain, it was not necessary to do this one. Okay, if you go ahead and do it, that's okay. It just proves that you can't use a negative there. All right, but if you look at our extreme value, this tells us that as we get more and more extreme, bigger and bigger, this value is going to get closer and closer to 0, but it will never reach it. So our range cannot include 0. And if we put in fractions, it gets really, really big. Well, this is a piecewise function, and often when that happens, the range will be in pieces, as it is here, because we have this one piece where p of r equals -2. If r equals 0, p of r equals -2. Or p of r is greater than 0. Time for application problems. To subscribe to satellite radio, a customer is charged a $15 activation fee and then is billed $18 a month. So there's going to be some cost to this customer. And it's going to depend upon how many months this customer uses the satellite radio service. So let's let our variable be m for month. And at the beginning, there's a $15 activation fee. And to that is added $18 for every month. So at 1 month, it will be $33. But let's say this customer is on a budget, and this customer decides to budget $200 for the year for his satellite radio service. Will he be able to have a whole year of satellite radio? Let's take a closer look at that. The function C of m equals $200, and we already knew that the function C of m was equal to $15 plus 18m. So if that's what C of m equals, then 200 equals that, and we just solve for the m. Subtract 15, subtract 15. Now we have $185 equals $18 times the number of months divided by $18, and we get the number of months to be 10.28. Even if that number had been a little bit bigger, say 10.7, we would still round to 10 months, because if he paid for 11 months, he would exceed his $200 budget amount. So this customer better either decrease other budget categories to increase this one, find a cheaper streaming service, or decide he doesn't really need satellite radio, or cancel after 10 months. Time for a new example. Ah, there's one. A city does not tax the first $20,000 an individual makes. Any annual income above $20,000 is taxed at a rate of 3%. We can now write a function, T of S, the tax on the salary. But we have two different situations here, okay? The city doesn't tax the first $20,000. If S is less than $20,000, then T of S equals 0. Okay, so it's 0 for any salary less than $20,000, and anything above $20,000 is taxed at a rate of 3%. Okay, that's not saying 21,000 times 3%. That's saying take the salary, subtract that first 20,000 from it, and then multiply by 0.03, because I have converted that percentage to its decimal equivalent. And as it says in the problem, this is for a salary greater than $20,000. Let's take a look at an example. Let's say someone makes $30,000 a year. Then this city would tax them at what rate? Well, $30,000 is greater than $20,000, therefore we will use this formula. So the S, the variable, the value of the variable will go in there, and then we'll multiply that by 0.03. The value of the variable is $30,000. That means this is $10,000. 30,000 minus 20,000 times 0.03. So we have $300 in tax that she will have to pay. Time for a final example, and we will do domain and range on this one also. All right, we're going to express the cost C of insulating a cylindrical water tank of height 2.0 meters as a function of its radius, r, if the cost of insulation is $2.99 per square meter, and the insulation is sold by the square meter, meaning you can't buy half a square meter. So we need to know the surface area of a cylinder, and that is equal to 2 pi r squared, which is equal to the area of the top and the area of the bottom, plus the height times the circumference. And I've included some diagrams to explain where that comes from. But for this instance, our surface area equals 2 pi r squared, we don't know the r yet, and our height is 2. So the second part of this becomes 4 pi r. That will be the surface area of these particular water tanks that have a height of 2 meters. The only difference between the water tanks will be the length of the radius. And since that is the surface area for any of these tanks of any radius but height 2 meters, the cost per whatever the radius is will be 2.99, that's dollars, times 2 pi r squared plus 4 pi r. Now, this is an application problem where I'm eventually going to have to fork over some money after I do this calculation, so I'm going to use pi approximated by my calculator, and I'm going to go ahead and distribute that 2.99 times 2 pi r squared and 2.99 times 4 pi r. Okay, since we're being practical here, I'm going to tell you that I'm imagining this water tank to be a water heater, and the smallest water heater you're going to find on the market, or the skinniest, the one with the smallest radius, will be about 0.23 meters. So I'm going to go ahead and tell you that the domain of this function is restricted such that r is greater than or equal to 0.23 meters. So I'm going to go ahead and put all real numbers in front of that, just so we keep that practice. So the domain of this function is all real numbers, r greater than or equal to 0.23 meters. Let's find the range. How can we find the range of this? Well, if we put in the smallest radius possible and then do the calculation, that will give us the smallest possible value for the function. Let's move this around a little bit. Get that up there out of the way a little bit. Okay, so our range now has to be greater than or equal to 9.64. And remember, that's in dollars because our 299 was in dollars per square meter, and we multiplied by the area, which is in square meters. Therefore, we are left with C of R is greater than or equal to $9.64 to insulate that tank. But because this is a math class, let's go ahead and put in our usual. All real numbers, so that the function C of R is greater than or equal to $9.64. This has been More About Functions, brought to you by Professor Rose. And maybe I should mention I'm using the Explain Everything software to make these videos. At any rate, I will see you in class. Please let me know if you have any questions.